This is the ethanol solution at a molecular level. Now, since it's a liquid, as you can see, the molecules are relatively free to move as they want. Now let's look at one of the molecules. As you can see, it's composed of CH3CH2OH, and, as the name implies, the H-NMR focuses mainly on the H atoms. This is the H nucleus composed only of one positively charged proton. And, like all atomic particles, it revolves around itself or its own axis. So, as a spinning charged particle, it generates a magnetic field mimicking that of a bar magnet with a north and a south pole. The magnetic moment, mu, of the magnetic field is calculated by this equation. Mu is equals to gamma IH divided by 2 pi. Gamma is the magnetogyric ratio, which is a constant for each nucleus, and for the H1 nucleus it's equal to 42.58 MHz per Tesla. I is the spin, which is equal to 1/2 for the H1 nucleus. NH is Planck's constant. As we can see, the nuclei are spinning and moving freely in random directions. However, when influenced by the magnetic field generated by the apparatus, they align themselves either with or against it. The ones aligned with the magnetic field are in a low energy state, in which they are settled and happy. The ones aligned against it, on the other hand, are in a high or excited energy state. It should be noted that the lower energy nuclei are slightly higher in numbers. The energy of both states is given by the following equation. B is the strength of the magnetic field, and M is the magnetic quantum number, which is equal to 1/2 for the low energy state and negative 1/2 for the high energy state. Therefore, we can also calculate the energy difference, or delta E, using this equation. Now if we shoot these aligned nuclei with a pulse of radio waves with a specific energy, some of the lower energy state absorb it and go to the high energy state. Then when the magnetic field stops, they emit this energy they absorbed. which is then interpreted by the receiver, and a band is drawn on the graph as a result. Now about the graph itself. The horizontal scale represents the chemical shift, delta, measured in ppm or part per million. The H-NMR shift ranges from 0 to 10. 0, or the right side, is called high field, and the left side, or 10, is called the low field. They can also be called the up and down field. As we move from left to right, the electron density around the protons increase and protect them from radio waves. In other words, it acts as a shield covering the proton, keeping it from absorbing radio waves. That's why the left side is also called shielded, and the right side is called deshielded. Now let's get to the action. We shoot the sample with successive pulses of radio waves with gradually increased energy. The very first band showing is that of the TMS, which indicates the 0 point of the scale. Then for the ethanol, we get 3 peaks with height ratio of 3 to 1 to 2. And since the height ratio is an indicator of the number of H protons represented by the peak, we can say that the first peak represents 3 H's, the second represents 1, and the third represents 2. Since the sum of the ratios corresponds to that of the actual number of H atoms in the ethanol molecule. Now if we zoom in on them bands, we notice that each one is split into several small peaks. The number of peaks is equal to n plus 1, where n is the number of alpha hydrogens, which are the hydrogens on the neighboring carbon. Now let's combine all of these clues to analyze the graph. First, we have 3 H atoms, which can mean CH3, and they are split into 3, which indicates that there are 2 alpha hydrogens, which means CH3CH2. Also from the band on the left, we have 2 H atoms, which means CH2, and they are split into 4, which means CH2CH3. Then in the middle, we have a single peak which represents the OH. Therefore, we conclude that this is the structure of ethanol.